All right, hi guys. I'm Amy, and as Sam said, I'll be talking about how we can rethink how we do indexing in the modern distributed data store. But first, before we get to any of that, we need to talk about what the secret sauce is that enables us to distribute a data store. So let's take your sort of traditional SQL table model, which has a number of columns associated with it. And a table consists of a number of rows, and these are the objects that you're replicating. Each row has a value associated with every column. Oops, that's an animation bug. And you have a number of partitions that make up your distributed data store, and the question is how you distribute these rows across all of your partitions. Traditionally, this is done by selecting a default column as your default partitioning key, k. Then you have some partitioning function, pf, that takes this value k and returns the partition that the row should belong to. There's a lot of different ways you can implement this partitioning function. Typically, it'll include some hash, so actually you're not going to be taking the partitioning function doesn't take k, it actually takes some hash of k. The partitioning function can range partition, for example, for locality. It can hash partition, like I said, to get rid of any hotspots, so you have some sort of uniform distribution. It can also implement something like consistent hashing, and this is good for elasticity. But that's not really the point of any of these. The main takeaway is that all partitioning functions are computing on some fixed key. And the fact that this key is fixed is a really big problem. And it's a problem because it makes secondary indexing a very hard problem in distributed data stores. And this is the problem we're going to be focusing on in this presentation. So what do I mean by secondary indexing? Just for the purposes of this talk, I'm going to define secondary indexing. I know this means a lot of different things for different people, but for the purposes of this presentation, it means providing fast access to data in your data store according to some column or set of columns that doesn't include this default partitioning key that you've used. So if you take our table model from earlier, a secondary index could be, for example, constructed over the purple column, or it can be constructed over the set enclosed by the blue box. So why secondary indexing? Well, secondary indexing is what enables a lot of the rich queries that you find in a traditional SQL database. This includes queries based on arbitrary columns, so you can do searches across all kinds of column values. It also makes joins a lot faster, because an index is able to isolate the rows that are relevant to your join very quickly. And also it can enable range queries. So why is secondary indexing hard in a distributed data store? So let's try an example. Let's do lookups by the primary index. So let's say we want like a select over rows where k is 4. And remember, k is your partitioning key. To identify the partition we need to go to, we simply plug this k value into our partitioning function, and this returns us some partition p. We go to that partition, and then presumably that partition is going to have some local index that helps us find the relevant rows. If we try to do the lookup by the secondary index, so let's select by some attribute other than k, and we try to identify the partitions we need to go to, we really don't have a value k to plug into this partitioning function. So we're at a loss here. And in fact, without k, we need to visit all the partitions in our distributed data store. This could potentially be hundreds or even thousands of partitions, depending on how big your data store is. So really, the problem here is that data is partitioned by a primary index that is completely different from the secondary index by which we want to do a lookup. So really what we have now is a data partitioning problem. This problem is actually unsatisfactorily solved in modern data stores. There are two main approaches, and the first approach basically doesn't address the problem at all. It doesn't address partitioning at all. It really just says, okay, fine, we've partitioned our data, and what we'll do is we'll just build local secondary indexes at each partition. So this is fine when you want to do an insert, because index updates are going to be local because your data is co-located with your index. But again, we didn't actually address the real problem, which is that lookups are now going to have to go to all partitions because no one partition contains a global view of your secondary index. And there's another bad thing about this, which is if you want to have some sort of consistency guarantee across these index lookups, you're going to have to do some kind of synchronization across partitions. The second approach does a little better. It tries a little harder to try to isolate the actual partitions you need to go to. And it does so by building a global distributed data structure that points into each of these partitions. So again, suppose you have your partitions, and you're going to build some sort of global data structure. And the reason why the top half of this tree isn't really on a particular partition is because you can actually implement this in a lot of different ways. For example, you can cache this top half at the clients. The top half of a tree typically doesn't change that much as the tree grows, so you might be able to cache it. You also might be able to put each of these nodes on a different partition. Or you might even replicate this top half at each partition so that you really only have to visit one partition, go down the tree, and then maybe go somewhere else for your actual leaf node. So this is bad because index updates could be multi-hop. If you have to go all the way down a tree, you have to sort of jump across partitions as you're walking down this tree. But like I said, it's good because index updates potentially don't have to go to every single partition in your data store. So it sort of attempts to solve the problem that we're faced with. But really, neither of these approaches are satisfactory. So now let's do a little thought exercise. What happens if we partition data according to every desired index? Again, this is a partitioning problem. The data isn't partitioned properly according to the indexes by which we're doing lookups. So what would happen if we partition data every single way? So you're going to have your default partitioning by your default primary key here, and it's going to use some partitioning function pf that takes k. Great. Now let's say we want to do lookups by the green column. What we mean by repartitioning the data really is we create a whole new partition based on the green index, and it's going to have a new, oh, you can't see that. Okay, well, it's going to have a new partitioning function, pf2, which takes column 2. You can't see that, but it takes a new value, which is essentially the value of the green column. And then if you wanted to do lookups over the blue index, or the blue column, you'll repartition your data again with a new partitioning function, pf3, that takes in the value of the blue column as its input. And you might also want to build local indexes at each partitioning so that you can make a local lookup fast. But again, that's really sort of a minor thing. What we want to do is narrow down the partitions that we actually have to visit. OK, but now we have a problem. Each partitioning needs to store the data again because it's a complete repartitioning of the data. So you can't have pointers into another partitioning of the data. And this obviously creates storage overheads. Why? Well, if you already have data replication in your system, which most real systems should, your data is already replicated 3 ways, right? And then you're going to go and create 2 additional copies of your data for the indexes that you want. So now your data is stored 5 times as opposed to the traditional 3. So this is storage overheads and network overheads. Furthermore, if you have some sort of availability requirement on your partitionings, suppose you want highly available indexes, you don't want an index to just fail and be unavailable, then you're also going to want to replicate each of these partitionings 3 ways themselves. And this is what your system is going to look like. So not only do you have storage overheads, you have to replicate everything 9 times, you also have network overheads because each insert needs to visit 9 different partitions instead of 3. And in fact, for those of you familiar with the system, this is the design of the system hyperdex. OK, so let's go back to our problem. So we sort of posed a potential solution to our problem. But as we saw, if we do this naively, then the overheads are going to limit the scalability that partitioning gave us in the first place. And in fact, in modern data stores, they often trade off this indexing functionality for scalability. A lot of data stores don't support strongly consistent secondary indexing. And now I want to introduce our system, Replex, which actually eliminates this trade-off by combining indexing and replication into a single protocol. So how do we do this? So we have a new replication unit, which we call a Replex. And a Replex is essentially a data replica that's partitioned and sorted with respect to some associated index. So in the diagrams from earlier, each of these sets of partitions are individual Replexes. And as you've probably guessed, it's called a Replex because it combines data replication and indexing. Naming is very important. OK, so what do we do in Replex? The main thing we observe is that we can replace traditional data replicas with this thing that we call a Replex. And by doing so, indexing comes free during replication. So here's how our system is set up. So suppose you have this table and you want to build 2 indexes. Then what we'll do is we'll create 2 replexes for you, 1 for each index. Now, to discuss inserts and replex, every replex is going to store every single row that's stored in the database. So the question is, which partition replicates a specific row? So let's say we have a client that's trying to insert a row, and it's going to need to do this once in each of the replexes. It's going to do so first at the purple partition, and it's going to take really the straightforward method, which is take the partitioning function that we described earlier and use that to identify the correct partition. Similarly, it's going to take the partitioning function associated with the green replex to identify the green partition at which it needs to replicate a piece of data. And for those of you who are familiar with it, you might be thinking, okay, yeah, this is like basically chain replication, right? And yeah, it's similar to chain replication. But there's a difference because each partition in chain replication is identical. So this is what the diagram would look like if we were doing chain replication, right? But in our replication protocol, you have to go to a purple partition and a green partition. And in fact, this means we need to modify our replication protocol with a commit bit.
Why is it the only one? Can it go to actually more than one?
No, because you're going to hash like whatever value is associated with the green column, and that's going to give you exactly 1 partition. Okay, so we need a commit bit. And what the commit bit really is, it just verifies that every partition you've visited has successfully replicated that row. So once you get to the bottom of your chain, each partition then sends a commit bit back up the chain that says that they successfully written that row. But because they're commit bits, that means they can be aborts. So when can a commit bit be an abort? Suppose, oh good, PowerPoint crashed. Okay, hold on, restart. Where's my mouse? How do I like jump to a slide? Space. Oh, okay, we can do that, okay. I probably should have gone from the back, but whatever. Okay, great. So commit bits can be aborts because suppose you have some sort of uniqueness constraint on the green replex that will cause your insert to abort. So namely, you've already inserted a row with that value. This will be, for example, if you consider the SQL table that we initially had, if you had created that green index with the unique keyword in SQL, for example. Okay, so if it aborts at that green partition, then you're going to have to abort it at all the partitions that you visited. So you have to send the abort bit back up the chain and back to the user so that the user knows that the write has been aborted. But the key thing here in pointing out what the replication protocol is that by the time the client receives this commit bit, not only has the system successfully replicated, or unsuccessfully if it's an abort, replicated that row, it's also indexed that row. So this is why we say indexing is free, aside from whatever overhead you have to pay for these local indexes that you're keeping track of on local partitions. But every indexing mechanism has to pay some cost for that anyway. But it's free because, so if you think about how other data stores do this, they run a replication protocol, then maybe in the background they have some indexing mechanism that's doing secondary indexing. Or maybe even you're doing this synchronously, so you do a replication protocol, then you have to go and update all of your secondary indexes. We don't have to do that. We don't have a separate indexing protocol. All you have to do is do replication, and then you also get indexing. And this is the power of combining replication and indexing into the same unit. Okay, so for completeness, let's talk about reads. Reads are pretty straightforward. You really just go to the replex that you want, and the idea is that you've already created a replex for the queries that you're going to see. You check for a commit bit, And obviously, if it's there, or it has to be there and it has to be a successful commit in order for you to return the row. Okay, so now let's talk about partition failures, because this is what actually makes Replex interesting. Suppose the green partition fails. When a partition fails, we're primarily interested in two things, which is how to, 1, rebuild or recover this failed partition, and 2, how to respond to client requests that would have gone to this failed partition. The key thing to observe is that the data is available, but the index is unavailable. That's the whole idea behind a replex. All replexes are data replicas, so your data exists somewhere in the purple partitions, but you have no idea where it is because your indexing information was in this green partition that you've just lost. So the question is, how do we find this data if this index is unavailable? We introduced this idea called recovery edges, and recovery edges are going to help us find lost data. A recovery edge connects two partitions that might share data. So in this diagram, the recovery edges emanating from the green partition are going to connect it to all of the purple partitions. Now, why is this? So suppose this was the partitioning function for the green replex. Then the rows that were stored in this dead partition looked like this. Basically, you could have had any value in all the other columns, but the green column has to have some value between A and F. And the fact that you have a star in the purple column indicates that any of these rows could have been potentially hashed to any of the purple partitions in the purple replex. So this is why you're connected to all the purple partitions, because you could have potentially ended up replicating to any one of them. So extending this logic, here's the complete graph of recovery edges for our system. And really, it's very straightforward to use these recovery edges to find data after failure. In fact, that's exactly how they're defined. So if this is your recovery edge graph, then you just go to the partitions that are edge connected to you. And those are the partitions you need to visit to find the data that you need for recovery. Okay, now let's sort of use this diagram to evaluate how we're doing during failure. So remember, we wanted to do two things. We wanted to both rebuild the partition and respond to client requests. We're going to measure these two things by recovery time and request amplification, respectively. Not respectfully. Okay, so in Replex as is, this is great for recovery time, right? Because we're basically parallelizing recovery across all the purple partitions. But this is terrible for request amplification because now we need to send all requests to every single purple partition. So the question is, how can we explore this trade-off between these two things that we're trying to deal with during failure? And the answer is something that we call a hybrid replex. A hybrid replex, you insert in between two replexes. So this is an example of a hybrid replex. And the power of the hybrid replex is that it enables flexible recovery edge graphs. So one recovery edge graph could look like this. Another one could look like this. And for the astute observer, the recovery edge that looks like the recovery edge graph that looks like this is basically when the hybrid replex is equivalent to just another purple replex. So what's great about having flexible graphs? The point is, every recovery edge graph becomes a point in your trade-off spectrum between recovery time and request amplification. Okay, so let's define hybrid replexes concretely. So recall the definition for a replex. It's basically a data replica that's partitioned according to some index. A hybrid replex, however, is not associated with a particular index. So if it's not associated with an index, then we don't really know how to partition it. And the answer is, it's shared across R replexes, and you partition based on the R replexes that you're shared across. And really what we mean by this is that the recovery edge graph is dependent on these R replexes that you've chosen. Okay, so that's like a little abstract, so let's make this more concrete. We can make this more concrete by considering how we insert into a hybrid replex. So again, let's suppose you have a client who wants to insert a row. So we're going to have to insert into each of these replexes. And we showed from earlier that all you have to do is like plug in a particular value into a particular partitioning function to find the green and the purple partitions. So now the question is, which hybrid partition are we going to go to? And if you consider the edges coming out of the green and purple partitions that you've already identified, you can see that they meet at a single hybrid partition. And in fact, this is the hybrid partition that's going to replicate your row. Okay, so there are a couple more nice properties about hybrid replexes, in addition to this trade-off that I mentioned. So let's first examine this trade-off that we get. If we add a hybrid replex to a traditional replex setup, then we get something like this. Then if you look at the purple edges, you see that recovery is less parallel, so we're parallelizing recovery across fewer hybrid partitions, but we get a lower request amplification. And in fact, some might argue that this is a little more important. You actually want your system to be available even after you've experienced a failure. Another nice property about hybrid replexes is that you can improve failure availability across multiple replexes. So to see this, let's consider how we would do this without a hybrid replex. So let's say this is your system, and you wanted to increase the availability of the purple partitions. Typically what people do is you add some exact data replica. So this is great, but if a green partition fails, that extra purple partition, or that extra purple replica doesn't help you at all. So in fact, if you want to increase the availability of the green replex, you have to do the same thing. You have to add another exact data replica. But this causes a 2x overhead in storage. On the other hand, if you can use a hybrid replex, you've basically increased the failure availability of 2 replexes only by inserting a single additional copy of data. So if the green partition fails, the hybrid replex helps you. And if the purple partition fails, the hybrid replex again helps you. So this is one of the key observations of a hybrid replex, is that if it's shared across R replexes, it increases the availability of all R replexes. So we've done this at 1.5x in storage, but as you saw, you get a little bit worse client requests because you do have some sort of fan out. You have a modest fan out instead of the one fan out that you would have had with exact data replicas. Okay, and now just some quick benchmarks. So we have 2 questions in sort of this eval section that we want to answer. 1, what is the impact of these replexes on steady state performance? And 2, how can hybrid replexes help us when there's a failure? For those interested, here's our benchmark setup. We have a table of 2 indexes, and we have a bunch of machines on the same rack. We benchmarked a couple of systems. The first is just a regular replex. We call Replex 2. The second is a replex system with a hybrid index, or a hybrid replex inserted. And the last is just the straw man design that I said HyperDex was, which is if it tries to increase the availability of a replica, it just replicates it 3 ways. So here's steady-state latency results. It's pretty clear that reads are supposed to be the same for both the Replex 3 and HyperDex systems because both of them are creating indexes on whatever queries are being asked in this benchmark. So that's fine. The key thing to observe is that inserts in Replex 3 take half the amount of time as inserts in HyperDex, and this is because we only need 3 network hops because we only have 3 replexes, and HyperDex has 6. Because you need to visit 6 replicas in the HyperDex case. We then failed a machine in one of our benchmarks. So we did a little steady state thing for like 25 seconds, and then we failed a machine. The first thing we want to look at is what happens to recovery time. So notice that HyperDex, which is the green line, recovers the slowest because it has tons more data than the other 2 systems, right? It's replicating data 6 ways as opposed to 2 or 3 ways. We also observe that Replex 2 recovers fastest because not only does it have the least amount of data, but it actually can parallelize recovery across all the partitions in another Replex. And this is what we were saying earlier. But we do see the trade-off in failure throughput. So Replex 2 has the worst failure throughput, and it's the blue line, because of this high request amplification. Now requests during failure have to visit all the partitions in another replex. On the other hand, if you add just a single hybrid replex, Replex 3 has failure throughput, which is essentially comparable to the throughput of HyperDex, which uses exact data replicas. So this means that adding a hybrid replex can do good things for you during failure. Okay. So in summary, what we've done is we've rethought the replication paradigm to include indexing. This means that indexing is no longer this really high overhead thing that we need to do in distributed data stores. And by replacing replicas with this idea of a replex, we can decrease not only the storage overheads of maintaining indexes, but also the networking overheads. And finally, this idea of a hybrid replex introduces a really new and rich design space for treating failures, for dealing with recovery, and dealing with steady state performance in distributed data stores. So yeah, are there any questions? Yes.
Yeah, you mentioned that with a hybrid replex situation, you have 1.5x space trade-off.
Mm-hmm.
How do you manage that? Does that mean only half of your data is being indexed as you scale?
Oh, no, sorry. Sorry.
Also, how does it scale as you add additional indexes beyond 2?
Yep. So to answer the first question, sorry, all I meant by 1.5 is you went from storing every piece of data 2 times to 3 times. That's what you do when you get the extra.
Okay, so rather than having the same number of hybrid replexes that you would have as other partitions, you would actually have like twice as many, like once for index A and once for index B. Like.
Yeah. So instead of replicating like A separately itself and then B separately itself, you have a hybrid replex that helps with the recovery of both. And then to answer your second question, yeah, that's a very good question. So a lot of the work we're doing now is basically figuring out if the number of indexes you want is like some I that's much greater than R, your replication factor, which is typically 3. Let's say you want 6 indexes. Then what you want to do is basically co-locate and stuff indexes onto the same replex so that, obviously lookups are going to be slower now, but you can still do clever things with partitioning that will narrow down the number of partitions you have to visit. So yeah, that's a good question. Yeah.
Hey, I read your paper a couple months ago and didn't realize you talked about this. So it's a great reading.
Cool.
So in the case where a hybrid replex fails, that doesn't impact anything on its own, right? You can still do the reads through both.
I mean, so yeah, that actually brings up a point that I sort of glossed over, which is that you may or may not actually direct reads to the hybrid replex in the steady state. You obviously probably should, otherwise you just have this replex just like sitting there being only used for recovery. But yeah, the idea is it can probably be used for sort of like, for if you have like an overloaded replex, you send anything else to the hybrid replex. And then when a hybrid replex fails, like whatever, you'll just send it somewhere else again. So.
But if you get both the hybrid replex and one of the originals fail,
Mm-hmm.
you should be 2 failure tolerant.
Mm-hmm.
Replicas, right?
Yes.
It still works, but you collapse to the original case with just.
Yes. Hmm?
As your data set grows, what do you do when the replex nodes run out of space?
Yeah, so this really depends on your partitioning function, as I said earlier. If you're doing consistent hashing, just like plug in more partitions, and then the hashing will take care of that for you. But yeah, that's a good question, because now you have to sort of like redraw the graph of recovery edges. But ideally, you would, like whatever you had originally would sort of stay where it is, and then you only need to migrate a very small amount of data.
As an implementation, how would it exist?
Oh, yeah, sorry, I totally forgot that. Yeah, so we did this on top of Hyperdex, because as you saw, Hyperdex is sort of very similar to the system. It just like does everything like 5 times more. So yeah, that's how we implemented it. But the point is, Replex is really an idea. You could, like, the underlying data layer can be anything. You can do this in SQL. You can do this in anything that requires data replication. You just have each replica be partitioned differently.
Leveraging Hyperdex's chain replication? Are they still doing chain?
Yeah, Hyperdex, well, I mean, in the code version that I use, they do chain replication.
Oh, okay, 'cause I remember seeing that they committed like Paxos in there a while back. I thought.
So they use Paxos for their coordinator, but I don't know if that,
That makes sense.
okay. Okay, yeah.
What are the implications of an update that would change the data where all the partitions for that row would have to change?
So I think that's just another insert. Right, like an update is really just an insert, if that's what you're asking.
Insert and a delete,
Yeah.
and you'd use the same
Mhm. Mhm.